everyone. I'm Meissha, a master student from University of Gajah Mada. In this video, I'll try to make a brief review for a paper in the field of analytical chemistry. This paper has already been published on ICS Sensor this year, so this is quite new research, and the topic is being tried now. These three people, Anju Fakber, Enrique Baron, and Roberto Delarita, create a paper-based analytical device which can be directly attached to the skin. The concept is this device can detect pH change in human sweat as one method to monitor health. By using microfluidic devices made from paper filter with polymer valves, which act as a door to open a way for the liquid going through different sensors. So miniaturization itself is a key current trend in analytical chemistry. And over recent years, there have been several developments to downsize three key elements here, which is sample preparation, separation, and detections. The microfluidic itself is a material in which have different properties with its macrofluidic or its bulk materials. The microfluidic itself is a science or a technology in which studying the behavior, which has the precise control and manipulation of small amount of fluidic, in this case is liquids and gases, in the scale of micro to even nano or picoliters. So it's different in the properties of surface forces, which dominate over volumetric forces. The flow also becomes laminar rather than turbulent in these microfluidics materials. And also molecular transport are going through a diffusion mechanism. So this is the microfluidic devices, which is the first truly microfluidics is in 1918s. This is the inkjet printers. And for now, in 2020s, the materials and microcomponents are used to tailor the technology to specific analytic functions, which can overcoming obstacles to portability and also cost efficacy, facilitating almost impossible experiment in the past, and also enhance the efficiency and at the same time also reduce the sample and the reagent use. For now, microfluidic itself has so many applications in the wide range of fields. Biotechnology and also pharmaceuticals is also important in vaccine development, in energy, in which is in this case is fuel cells, also in chemical industry and nutraceuticals or food. So, scientists now struggling how can microfluidics connect to the human body. So the incompatibility between solid electrical components and the human tissue, the flexible dynamic nature is another challenge which is need to be overcome here. So scientists now provide some solution to overcome this. They use paper-based analytical devices so they can attach directly to the human body. They use filter paper with dried polymers as closed valves and then connect it to skin. So this is called as microfluidic embedded in skin adhesive. They use also the method called as Chrono-Sampling here, which is absorbed sweats directly from the skins. They use also mechanism called as colorimetric signal transduction, which measure the change in color based with the change in the sweat pH. They will got the rate of sweating and electrolyte concentration fluctuation over the times. So in brief, they got the results is a multi-sensor paper can measure 9 consecutive pH at the same times. They also can adapt these devices to urea biosensor, in which they can detect pH, which generated by the hydrolysis of the analyte caused by urease enzyme, which can convert urea to carbon dioxide and also ammonia. The last one is the analytical platform can also monitor the pH of sweat, and in this case, they have been compared it with laboratory-based methods. And they take sample from volunteers during an exercise routines. So this the first reason why they use a filter paper. The filter paper itself can absorb sweats and transport it to the sensing area. Also, they can bendable and or can be folded, and also they are flexible. The Dissolvable paper is also can be used as a sensing patch. And also the advantage of colorimetric signal is they don't need to use circuit or antenna to connect between human body and the devices, because the test outcomes can be recorded using this camera or smartphone directly. And in this case, they are so wireless because they just use color as an output to read the results. And so this is the mechanism of how these devices work. So the Chrono-Sampling itself means that they measure samples sequentially or continuously over the time. So chrono itself came from Greek words, which mean sequentially or continuously. So this is the inlet, and fluid transport is blocked with this polymer. So they cannot go through the sensor alpha, and they're going through the sensor beta. As the fluid flow to the polymer dissolve over time, and the valve start to get thinner here. And after certain time, the valve completely dissolved, and so the sample can go into to the outlet, to the sensor B, and to the sensor alpha. This is the picture of the first devices, which is do not use valve here. So they don't block the alpha sensor here. So the green ink here is going through to the alpha and to the beta circular part in the same times. And if they add dissolvable polymer valves here, it makes the green ink deflects to right, so they can analyze the composition of the green ink first. At the end, if they increase the number of valves and sensing element is the same as they increase the accuracy of sequential measurements here. And that's why, because the time between measurement is then reduced. And how they make this multi-sensor? They make it for Whatman filter paper. And it is drawn with Adobe Photoshop and then cut by hand to produce microfluidic devices. And then they use universal pH indicator by adding this 1 microliter drops to the circular area, and then each drops dried at room temperatures. Then they add next drops until 4 times. Using less than 4 drops or the 4 times steps will reduce the sensitivity at the high pH values. It's because from this plot, we can see it's in the 4 drops with the green line here, they're still stable at the high pH. And the last one is the soluble valves obtained by adding PSS. This is the structure of PSS, and this is the structure of PVA. They added each half microliter drops to the platform, and then dried in oven at 35 degrees Celsius. And after that, they got soluble valves. This step works better than drying at room temperature. And for this platform to be attached in the skin, to be able to attach in the skin, they use this adhesive medical grade. The first prototype is consisting 2 channels here, so alpha and beta. And this is the inlet in the top part, and the outlet is in the squared area. So the sensing element, alpha and beta is blocked by PSS here. So if the sample going through the inlet, it will deflect it to alpha, and the alpha will be filled up first. And the ability to deflecting liquid, it's what makes the polymer better suited in these devices. And this is the picture if PSS varying based on its concentrations. And also, this is the time-dependent liquids flow from top to bottoms. So at 2.5 minutes, only alpha circular here is filled up. And after 6 minutes, the green ink start to fill up the beta sensor here. So it means that the PSS start to get thinner, and the green ink start to coming through to the beta circular part. So in conclusion, if the percent PSS increase, the time required to fill beta is also increases. The valve opening time is difficult to control with the precision. So the solution is by drying PSS at 37 degrees Celsius. And this is the plot made to check time required to fill up the circle area. And the relationship between filling time and percent PSS here is linear. Why this works for alpha circular, which is independent from valves. We know here that alpha is blocked with valves. They just fill up in 5 minutes. And this is the second generation of microfluidic devices. They're able to performing 5 sequential measurements here. This experiment is increasing the ability of pH measurement, and also at the same time increase complexity. So here, the PSS is put here, blocked to the all for a circular area and only directed to the alpha. And this is what they got with picture, and the green ink directly going through to the alpha circular the sensor. So this is the order of area. So first is alpha will be filled first, and then the second is beta. Here it is a beta, and then gamma, and then delta. This one is lambda. So all in 10 minutes. So this is the plot that have been made without polymer falls and with polymer falls here. With polymer falls, they got a linear line here, which is increased along with filling time from alpha to lambda. But without polymer falls, the alpha here fill up first, and then another 4 fill up at the same time. The next is 3 generation of microfluidic devices. Here they perform 9 sequential measurements. So they compare both by using polymer PSS and polymer PVA. Sequential pH change within 2 minutes might not be detected properly. So the chrono-sampling with these devices is not precise enough to separate them. So red line with polymer valves, and then black is without polymer valves. And the next one is, this is without local outlets here, and this is with implementing local outlets at strategic position. This is the outlet here with from like TNGL. So they got 2 plots here, and this is come by challenging the multi-sensor with a sequence of solution. The first is from pH 7 to 5 and then back to 7, and the second one is from pH 5 to 7 and then back to 5. For the first one, they got this plot, and for the second, it cannot be measured accurately because they have large depth volumes. The solution is to increase the number of sensors and again redesign the valves. So by using the local outlet here, they have the higher accuracy. So how this local outlets works? It can be seen in the C. The outlet's function is to help evacuate before the solution reach the sensors. And also they can here reduce the amount of mixed sample in the sensing area. And then they increase the measurements times here. The idea of this experiment is to change from pH multisensor to biosensor for urea monitoring by adding the urease. Urease itself is a catalyst to convert urea to become ammonia and with the other products, carbon dioxide. So this is the 3 plots that they got. So by analyzing to the 3 plots here, the proposed microfluidic platform is so suitable for developing wearable biosensor. And also the next is sweat measurements. The idea is to take the adequacy of the devices and pH of human sweat during exercises. There is 3 plots here. So this is the first one that only wear 1, while the second one that wear 2 at the same time. And for the second volunteer, they got fluctuative results here. Means that different sensors yield similar results when tested under similar condition, because here we got an average 6.3 and here is 6.3 also. So the minimum and the maximum, the fluctuative value is different. This is the minimum is 6 and the maximum is 6.3. Here is 6.1 to 6.7. And for laboratory method itself, they yield 6.5 to 6.7 with the average of 6.5. In all cases, the reference method itself yields pH values more than 0.2 units than the paper-based platform. So this is more than 0.2 between this and this. And so for the future design itself, they have prospective application here. This is for professional athletes, for neonatal care settings, and also for patients recovering from stroke. And in the future design, they need to implement different biosensors in the platform. Also change the dimension and the number of local outlets in the microfluidics designs. The last one is they add more sensing element in the design or in the circular area, which could further improve the accuracy. So this is the end of my presentation. Thank you for the attention.